Hi everyone, welcome to this machine learning and meaningful game seminar. Thank you for joining. So today it's our great pleasure to have Aditya Mahajan, who is a professor of electrical and computer engineering at McGill University, and he's going to present his work on reinforcement learning in stationary meaningful games. So thank you very much, Aditya, for accepting to give a talk, and the floor is yours.
Thank you, Matthew. Thank you for the introduction and thank you for the invitation. It's a pleasure to be speaking here. I'm going to be talking about reinforcement learning in stationary mean field games mean field interactions arise in various applications ranging from communication network, transportation network, power systems, robotics, and others. And the importance of mean field interactions have led to various models of mean field games and teams. The previous two talks in this series did an excellent overview of the different formulations. So I'm actually not going to go over that in detail. I'll present a specific model for mean field games, which is known as stationary mean field games. And I'll talk about the two different solution concepts for this in the competitive or strategic scenario, which is the stationary mean field equilibrium, and in the cooperative scenario, which is stationary mean field social optimality, and talk about local solution concepts for these. And then I'll describe a simple idea for doing reinforcement learning in such mean field models, and conclude by presenting examples from malware spread in networks, but actually there should be another bullet here on between investment in firms in an industry. So let me start with describing the model. So we're looking at a population of n homogeneous agents. I'd like to emphasize that I'm restricting to homogeneous agents just for simplicity of the presentation. Everything here generalizes to the case when there are heterogeneous agents where each agent has a separate type. I'll assume the state space and action space of all agents are identical, denoting that by S and A respectively. And for agent I at time t, SIT denotes the state and AIT denotes the action of the agent at time t. I'm going to assume that there is mean field coupling. And what I mean by mean field in this talk is the empirical distribution of the states of all agents. And I think like a nice way to think of this is to think of this diagram as a color swatch. So these are 15 cross 15 agents, and each agent has three states, red, blue, or yellow. And this bar at the bottom represents the fraction of agents who are in blue, fraction of agents which are in yellow, and fraction of agents which are in red. And that is the mean field of this population state. We look at mean field coupling in both the dynamics and the reward. The assumption for the dynamics is that the next state is distributed, next state of agent I evolves in a controlled Markov manner depending on the current state of the agent, the current action of the agent, and the mean field of the population. I'm also going to assume that the per step reward which agent I receives depends on its current state, its current action, the next state that it goes to, and the population mean field. And we'll consider the expected discounted reward setup. So the valuation or the utility for player I starting from state S is given by the expected discounted total reward over an infinite horizon. Simple observation here is that if all agents play a Markov strategy where each agent chooses its action as a possibly randomized function of its current state, then we can write down the evolution of the mean field by just following the law of total probability, which is averaged over the current state of the agent, probability that the agent chooses a particular action, and the probability that the state evolves to the next state. This is effectively the discrete time Fokker-Planck equation, and I'll be using this quite often, so I'll just follow the notation saying that when players at time t follow strategy pi t, then the mean field at next time step is a function phi of the current mean field and that policy. So I'm going to be focusing on what's known as stationary mean field equilibrium in this strategy. This is a solution concept which was proposed by Weintraub et al. In a series of papers in the mid 2000s. And this has been, they were calling this oblivious equilibrium, and it was called stationary mean field equilibrium in paper by Adlakar, Johari, and Weintraub, and they also generalized the conditions on existence and also notions of optimality for this setting. This is contemporaneous work to what was called evolutive solution concept in the talk by Matthew and Sarah last week, which is the work by Huang, Malhame, and Keynes, and Larcy and Leons, which considers a solution concept in which agents are reacting to a trajectory of mean field, while in stationary mean field equilibrium, agents are reacting to a stationary mean field. And I'll make this distinction clear a bit later. So traditionally in the literature, the way to interpret stationary mean field equilibrium is that it is presented as an approximation to Markov perfect equilibrium. So one imagines a scenario where we have a game where agents observe the state of all players. And in that game, due to complexity reasons, agents may decide to play a strategy which only depend on their own local state. And it's typically shown that looking into these restrictive class of strategies only leads to an epsilon loss in optimality. So one can get epsilon Nash guarantees for looking at these types of equilibrium concept. This is the similar notion which is used in the evolutive mean field game, which is also presented typically as an approximation to a Markov perfect equilibrium. However, I think that there is another way to interpret stationary mean field equilibrium, and that's how I'm going to present it in this talk. I'm going to view a stationary mean field equilibrium as a sequential equilibrium of a game with imperfect information. So to explain that, let me do a very quick review of extensive form games. And let's start with extensive form games with perfect information. For simplicity, I'll just explain this in games defined on game trees for finite horizon, but similar notion works for games with continuous state and action spaces and defined over potentially infinite horizon. So let's consider a game like this. A strategy is for every node, which is a player is acting at a node, we tell what action that player would take, either a pure strategy or a mixed strategy where the player would randomize between all possibilities available to it. We do so for all players at all nodes of the tree. This would constitute a strategy of this extensive form game. One can do a normal form reduction of the game. That is, enumerate all strategies of all players. So let's say if I had this two-player games, I could list all possible strategies for player one, all possible strategies for player two, and for every pair of strategies for player one and two, I could compute what is the payoff for player one and player two and get the bimatrix representation. So the standard notion of Nash equilibrium in this setting is to do the normal form reduction of the extensive form game and look at Nash equilibrium of the normal form game. And any Nash equilibrium of the normal form game is a Nash equilibrium of the extensive form game. This notion is not ideal. And part of the reason is that this gives rise to non-credible threats. So this gives rise to situations where if player one is playing at this node and is planning to play this action, player one can, in the Nash equilibrium, propose whatever it wants to do in these nodes. But if it actually gets to play in this node, choosing this move might not be locally optimal. So player one is making a threat which is non-credible. So overcome this limitation, the standard solution concept for extensive form games is what is known as subgame perfect equilibrium. So what we mean by a subgame is, let's consider player two at this node. So the subgame would be the part of the game tree which lies below the player 2 at this node. So everything which happens in this part of the game tree. So a strategy profile is called a subgame perfect equilibrium if it is a Nash equilibrium of every subgame. So if we look at the subgame starting from this node, it should be a Nash equilibrium. Subgame starting from this node, it should be a Nash equilibrium, and same for every other node. This rules out non-credible threats, because when we start in any particular subgame, we have to play strategies which are Nash equilibrium for that subgame. And subgame perfect equilibrium can be identified using dynamic programming. Markov perfect equilibrium is a special case of subgame perfect equilibrium, where if we have a Markovian dynamics, the assumption is every player plays a Markov strategy that gives rise to Markov perfect equilibrium. Now, when players do not have complete knowledge of where they are in the game tree, these are known as games with imperfect information. Typically, these are represented by drawing these information sets around nodes. And this means that in this particular information set, player 1 cannot distinguish whether it's on this part of the game tree or this part of the game tree. So information set is just nodes of the game tree which are indistinguishable to a player. And since player cannot distinguish between them, it must play the same action on all nodes which lie in an information set. Now, when we try to define something equivalent to subgame perfect equilibrium in games with imperfect information, there is a difficulty. And that is, if I look at, for example, the subgame starting from this information set, and I want to compute what is the expected performance of, let's say, this strategy, I need to know what is the probability distribution of being in both the nodes in this information set. So in order to do that, players need to have a belief on all nodes in an information set. That is, when player 1 finds itself in this information set, it needs to have a belief on what's the probability it's at this node and what's the probability that it's at this node. Because of this, the notion of solution in games with imperfect information is a bit more involved. The most common solution concept is that of sequential equilibrium due to Krebs and Wilson, who define a sequential equilibrium as a pair of a strategy profile, which is what each agent does at each information set, and a belief system, which is what each agent believes is the probability of the nodes in each information set, which satisfies two properties. The first property is sequential rationality. That is, when we look at any subgame, and if we evaluate the expected utility of the player playing the subgame according to his belief on the information set, then the strategy that the player is playing in this subgame should be a Nash equilibrium. And the second is consistency. That is, the beliefs of players are updated in a manner which is consistent with Bayes' law. So most other solution concepts in games with imperfect information, like Bayesian perfect equilibrium, is a special case of sequential equilibrium. And other refinements of sequential equilibrium are also considered, like trembling hand perfect equilibrium and others. A key limitation of sequential equilibrium is that it cannot be computed using dynamic programming. It requires solving a forward and backward consistency equations, and this is difficult to compute both for finite and infinite horizon models. In fact, except for some very, very simple cases, there are no general algorithms known on how to compute the equilibrium. Now, having gone over this review, let's come back to the mean field game. And I'm going to claim that the notion of stationary mean field equilibrium is a sequential equilibrium of the mean field game in the following sense. So stationary mean field equilibrium is a collection of a strategy profile which tells each player how to act at each state of the game, and a mean field belief, Z, which satisfies two properties. First is consistency. That is, the mean field should be the stationary distribution that we would get if all players play that strategy profile. So this implies stationarity of the beliefs. The second is we evaluate the performance of any particular strategy according to this belief system. So when player I is evaluating the performance of policy I, given a belief system Z, starting from state S, it assumes that it will choose actions according to that strategy. States would evolve according to his given beliefs on how everyone else's state is distributed, and he would compute the expected discounted return according to this. Notice what has happened is that what we had here was Z of t, but because of starting with this belief that the distribution is stationary, while evaluating something, the player assumes that instead of Z, he has the stationary mean field distribution here. So what this amounts to is that players are evaluating performance according to their belief, as they should in a sequential equilibrium. And once we have this, we would look for sequential rationality, that is the player's evaluation for policy pi, assuming belief system Z, should not reduce if it deviates to any other strategy pi star. So if we have this is sequential rationality. So a combination of consistency and sequential rationality, where the beliefs are computed according to assuming stationary, where the valuation performance is computed assuming stationary beliefs, gives rise to a stationary mean field equilibrium. Before I move on, are there any questions here? Okay. All right. So once we have this notion, we can also consider the situation where players are cooperative. And in the cooperative setting, we can evaluate the performance of a generic agent in the same manner as before. So players again make the same assumption that other players are distributed according to the stationary distribution, and based on that assumption, evaluate the future performance of any strategy pi. Now, instead of asking for consistency and sequential rationality, the notion would be that of optimality. So we say a strategy profile pi is optimal if deviating to any other strategy does not improve performance. But the difference from sequential rationality here is that the stationary distribution with respect to which we are evaluating the performance depends on the fixed point of strategy pi in this case, but when we deviate, it depends on the fixed point of strategy pi prime. So I want to emphasize that the notion of equilibrium and social optimality are different. For equilibrium, deviation in policy does not change the stationary mean field. And the reason is because we are viewing a single player who's deviating from the prescribed strategy. In case of optimality, deviation in policy changes the stationary mean field because the assumption is that the entire population is deviating in its policy. So that gives rise to a different mean field. Okay. So what I'm going to do now is look at these two solution concepts, that of stationary equilibrium and stationary social optimality, and refine them a little bit, and then think of reinforcement learning for achieving these equilibrium. So one of the challenges with working with these notions of equilibrium is that these are a global solution concept. Checking whether a strategy profile and mean field is in equilibrium or not requires a search over all other policies. There is also the usual curse of dimensionality, that in order to verify whether something is in equilibrium or optimal, I have to compute the performance of expected future rewards for a given strategy profile. And if my state space is large, computing such value functions is computationally difficult. So to avoid these two challenges, instead of looking at global solutions, we would propose to use local search over parameterized policies. And I'll explain this later on. And instead of computing exact value functions, we can use function approximations to compute them approximately. So let me start by describing the local versions of the solution concepts. So I'm going to assume, to simplify things, I'll scalarize the returns. So I'll assume that the initial state is distributed according to some distribution. This is the start state distribution, and this is independent across agents. And I'll compute a scalar return for a generic agent playing policy pi and assuming stationary mean field z as the expected return of the value function. Sorry, there's a typo here. This should be value function evaluated at S naught, distributed according to this distribution sign. And I'll also assume my policies are parameterized by some parameters theta, which lie in a closed compact set. So we can think of that as softmax policies. With this setting, we can talk about local stationary mean field equilibrium. So a pair of policy and mean field is a local stationary mean field equilibrium if it satisfies local sequential rationality. And by local sequential rationality, I mean that if I fix the mean field and think of the partial derivative of the performance with respect to the policy parameters, that should be 0. And consistency is that the mean field should be the solution to the Fokker-Planck equation for that policy. That is, it should be the stationary distribution that I get when all players are playing that strategy by theta. We can also define local stationary mean field social optimal strategy, which is a strategy which satisfies local optimality. The difference in local optimality is I'm not thinking of partial derivative with respect to the policy parameters. I'm looking at the performance where both the policy and the corresponding mean field depend on the choice of the policy parameters. And when I think of deviations in the policy parameters, both of them change, and that deviation should be 0. And this z theta here is the stationary distribution of pi theta. These two concepts are different, and let me just explain what the difference is. So recall that the full derivative of a function of two variables could be split according to the chain rule. The first term is what we want to be equal to 0 for local optimality. The second term is what we want to be equal to 0 for sequential rationality, which is just the first part of this total derivative. The total derivative also has another term, and in general, this second term is not 0. And because of this, the local optimality equations are different from sequential rationality equations. So local stationary mean field equilibrium is not the same as the local socially optimal solution.
Excuse me.
Sure, yeah.
Sorry for the interruption. I think that there is a question in the chat by Levon, who is asking if, given a policy pi, do we know if the fixed point z is unique, or in general there could be? I imagine there could be multiple.
There could be multiple. For most of the existence results, one assumes that we are restricting attention to strategies which lead to unique stationary distributions.
Okay, I see.
So if I'm thinking of softmax policy, I'll always assume that there is no deterministic action. So everything is chosen with some positive probability. So my Markov chain is aperiodic, and I would get a stationary distribution.
Okay, thank you very much.
Any other questions? Okay. So let me now talk about reinforcement learning in this setting. And the idea is really, really simple. I have parameterized policies. So I could think of a gradient descent or gradient ascent method to update my policy parameters, where I follow an iterative process where I update my policy parameters as my old policy parameters, plus some learning rate times g of theta k zk, which may be viewed as an unbiased estimator of the partial derivative of performance with respect to the policy parameters. For the time being, let's assume I can get this in some way. So if I could get that, I could just follow this recursion to update my policy parameters. And the notation square bracket subscript theta means I'm projecting them back into my closed compact set theta. And I will simultaneously update my mean field. So the new mean field is the old mean field plus beta k times an estimate of the stationary distribution if I follow strategy pi theta k minus what my current the current distribution was. So this difference is some form of an estimate of the gradient of the stationary distribution. And here by theta hat k, I mean an unbiased estimate of the stationary distribution that I would get if I follow policy theta k. And if I look at these two learning rates and I choose them such that the ratio of these two learning rates go to 0, plus these learning rates follow the standard Robbins-Monroe conditions, that would mean that I'm saying that the policy parameters are being updated at a slower time scale, and the mean field is being updated as a faster time scale. And that's the reason why beta k becomes much, much larger than alpha k. Then under standard technical conditions, I can argue that the pair of theta k zk would converge almost surely to a local stationary mean field equilibrium. So from a conceptual point of view, developing a reinforcement learning algorithm is relatively straightforward. The challenge is understanding how do we get these unbiased estimators for these two things, and how to actually choose the learning rates in practice to make sure that the algorithm converges. So looking at these practical considerations, the first thing to note is that two timescale algorithms are very nice from a theoretical point of view because they make proofs very simple, but they are very hard to, it's very hard to get them to work in practice. And in practice, what one often does is rather than changing the learning rates of the slower and faster timescale, we just fix the ratio of these two learning rates. Or equivalently, I can think of that as that for every iteration of the slow timescale part, which is the update of the policy parameters, I would run multiple rollouts of the fast timescale part, which is the update of the mean field. So if we take this view and say that we are running multiple rollouts of the mean field update, this can effectively be thought of as computing the stationary distribution of this mean field system in a particle filter-like approach. I consider that there is a population of particles. Each particle is following the strategy pi theta. I start with some initial distribution and let the system run for a certain burn-in period. And whatever distribution of particles I get at the end of that is an unbiased estimate of the stationary distribution of the system. So if we can do that to compute theta hat and choose the timescales of this algorithm, so the only thing remaining is how to choose the gradients. And there are two ways that we can choose the gradients in the equilibrium setting. One is to use likelihood ratio-based estimates, or what are also known as score function-based estimates. One can show that the gradient of the performance with respect to the policy parameters is given by the following discounted return, which is the discounted return multiplied by the gradient of the log of the policy multiplied by the cost to go from that point onwards. This is exactly the same as the policy gradient formula in reinforcement learning, and the proof is also exactly the same. And the reason for that is once I fix Z, the performance of a single agent is effectively same as what we have in standard single agent RL setting. So all that is changing is that I have Z dependence in evaluation of this value function. But apart from that, the formula looks exactly same as what we have as policy gradient in RL. Another method to do estimating gradients is to use simultaneous perturbation-based estimates. In this, I choose a random variable eta and a small constant c, and I evaluate the performance of policy parameterization theta plus c eta and theta minus c eta. These, for example, could be evaluated using Monte Carlo. Then this particular formula gives me an unbiased estimate of the gradient of the function. In particular, if I choose the vector of etas as uniform plus minus 1, this gives me simultaneous perturbation stochastic approximation. If I choose them as Gaussians, this gives me smooth functional stochastic approximations. This is useful if my policy was not differentiable with respect to the policy parameterization, then I can still use simultaneous perturbation-based estimates to get an unbiased estimate of the gradient. Similar idea works for the socially optimal setting. The only difference is that we don't have likelihood ratio based gradient estimates there. And the reason for that is, as I said here, the reason we can get likelihood ratio based estimates is because my Z is fixed. In the socially optimal case, I also have to take the derivative with respect to Z. So I would have a term in evaluating the full derivative, which would be the derivative of the stationary distribution with respect to the policy parameterizations. And that is something which is very difficult to characterize. We could not find anything in the literature which gives the sensitivity of the stationary distribution of a Markov chain with respect to its transition probabilities. But if someone knows something about this, I'll be happy to discuss that further. And that's the only reason we don't have likelihood ratio-based gradient estimates in the socially optimal setting. So this sort of is the high-level review of the reinforcement learning side of things. Before I move on to examples, are there any questions? Okay, so I'll present two examples. The first is an example on malware spread in networks. This was when we initially wrote the first version of the paper, which was in 2018. This was there. If we were writing it now, you could all guess what this example would be now. But we are assuming there is a network of agents, which could be either in a healthy state, which I'll denote by 0, or in a non-healthy state, which I'll denote by 1. And there is a continuum of states which are in between. And the higher the state of an agent, it means less healthy it is. So we have a population of such agents, and there is a mean field of this, which is different agents in different states. And the model consists that each agent has two actions. They can either do nothing, or they can take a repair action, and we'll denote this by 0 and 1. If the agent does nothing, the state of the agent deteriorates over time. So if it was healthy, it starts getting less and less healthy, and which less healthy state it goes to is given according to a controlled Markov transition. If the agent takes a repair action, no matter which state it is in, it resets back to a perfectly healthy state. The per step reward in the do nothing case depends on the state of the agent and the mean field of states. And in case of taking a repair action, it's again something which depends on the state of the agent, the mean field of all states, plus there is an additional cost that the agent has to pay to take a repair action. So this model is a representative model for problems which have positive externalities. There is the free rider problem here. That is, the agents get good reward if the population is in a healthy state, but to reach a healthy state, each agent has to take the repair action, which is costly. So should the agents take a repair action or just freeload on the fact that other agents are making an effort, and that would keep the population state healthy. So in particular, we look at reward functions where the reward is some constant times the state of the agent, where this constant is some universal constant plus something which depends on the average of the mean field. What I mean is if I look at the average value of the state of all agents minus a cost lambda which agents have to pay if they take the repair action. It is known for this model that the stationary mean field equilibrium is unique and is given by a threshold type strategy, which is that the agents take a repair action wherever their state is deteriorates more than a particular threshold. So to run numerical examples in this thing, we considered two policies. One were threshold-based policies, where threshold was a real number between 0 and 1. When we consider threshold-based strategies, the strategy is not continuous. This means that we cannot use likelihood ratio-based estimates, so we have to use some other estimates, and therefore we use the simultaneous perturbation stochastic approximation estimates here to compute the grade unbiased estimate with respect to the threshold. We also looked at neural network-based policies, and in this we computed the gradient using the likelihood ratio-based estimates using reinforce minus a baseline, which is a standard algorithm to compute likelihood ratio-based estimates in reinforcement learning. So this is the performance of these systems. So first look at the setting when we have strategic agents. I'm showing three curves. The straight line is the stationary mean field equilibrium, in this case, which can be computed exactly by solving an analytic equation. The blue curve is showing the convergence of the threshold-based strategies. The band here shows that we initialize it with different random initializations, and these are, I think, 100 different initializations. So this is the 75th percentile and 25th percentile error band as we go along different sample paths. And the yellow one is the same thing for neural network-based strategies. And as one can see, both FPSA and likelihood ratio-based estimates, both of them converge relatively quickly to the right performance. In case of cooperative agents, we cannot do the computations with neural network-based strategies because likelihood ratio-based estimates do not work here. So we are restricting attention to threshold-based strategies, and they also converge relatively smoothly to the final socially optimal value. And note that the equilibrium solution has a different performance in the socially optimal solution as one would expect in general. In this case, we can also compute if for the threshold-based strategies, if the thresholds are converging to the right solution, and we find that they are. We can also see whether the mean field is converging to the right solution or not. Mean field is a vector, so I'm scalarizing it and plotting the average of the mean field. And both for strategic agents and cooperative agents, the mean field also converges to the values predicted by theory. So this shows that the reinforcement learning algorithms are working reasonably well in this simple toy model. I'll also consider another example, which is of investment in product quality. This is adapted from a model presented in Weintraub et al. This considers investment decisions of firms in a fragmented market. Each firm has P products. There is a quality of each product, which is a real number between 0, 1. So the state space for each firm is a p-dimensional vector, which indicates what is the quality of each product that the firm is producing. For each product, the firm has an option to either invest in that product or not invest in that product. And so the action space is a discrete space with 0, 1 to the power p. And the dynamics and rewards are coupled through the mean field of what's happening with what are the investment decisions which everyone is making in the industry. I'm not presenting the specific form of these couplings because those are not important for the purpose of this talk. We consider a simulation result where we consider 3 products, and we consider neural network-based policy parameterization. And we noticed something interesting here, that when we ran the simulations, it appeared that we had very high variance. And so we went back and checked the trajectories more carefully. And what we did was we looked at the trajectories that we are getting, looked at the tails of those trajectories, and clustered them. And what we observed is that there were actually 2 stationary mean field equilibrium in this case. And some of the sample paths were going to the first equilibrium, and some others were going to the second equilibrium. And this is perfectly reasonable because in general, stationary mean field equilibrium is not unique. There can be multiple stationary mean field equilibrium. The local stationary mean field equilibrium is also not unique. There can be multiple local equilibrium. And what we are finding is that in this particular example, there are 2 equilibrium, but the RL algorithm, some of the sample paths do converge to, each sample path does converge to one of the 2 equilibrium. With this, I'll conclude. I think the key takeaway message that I'd like everyone to take with this talk is that learning in large games and teams can be easier than those in small and medium ones. So there is a lot of work in multi-agent reinforcement learning for small number of agents, and also games with imperfect information with small number of agents, or decentralized control of systems with small number of agents. And all these problems are really, really difficult. But when we get to systems with large number of agents with some form of symmetry between the agents, mean field approximations make it possible to have scalable planning as well as learning solutions. In this talk, I focused on the stationary mean field games. This provides a different way of looking at mean field games. As I said in the beginning, I presented everything for the homogeneous case, but all the results extend easily to the heterogeneous population, that is agents with multiple types. And a very simple way to think of this is that I could just extend the state space and think of type as a component of the state, which does not evolve with time. So I can think of this as just a system with multiple types can be viewed as a homogeneous system where types are part of the state space. One interesting thing which I did not delve into, and there is not too much there in the literature about that, is the comparison between stationary mean field games and evolutive mean field games, borrowing the terminology from the previous talk. So note that from a practical point of view, both planning and learning solutions in the stationary case have significantly lower complexity than their evolutive counterparts. And the reason is that in the evolutive mean field games, we are looking at strategies which are evolving over time. The strategy is not a time homogeneous strategy, but it is a trajectory of strategies. While in the stationary mean field case, we are looking at a stationary strategy or a time homogeneous strategy. The reason for that is that in the evolutive mean field games, players are playing their best response to the trajectory of mean field. While in the stationary mean field games, we assume that based on this notion of sequential equilibrium, each player has a belief that the system is stationary, and that means they only have to play a best response to a stationary mean field, and that best response is also time homogeneous. However, this simplicity on the computational complexity level comes with requiring stronger conditions for existence of equilibrium. And that is completely natural. I want to now establish existence of equilibrium where the policies converge to a fixed point and players are playing best response to that stationary distribution, while in the evolutive mean field games, the requirements are more relaxed. However, the final thing there is how do these two compare in terms of their efficiency? And as far as I know, there is no detailed comparison between the two, and I think that would be interesting to study, that what's the performance difference between stationary mean field games and evolutive mean field games, or some of these simple examples. With that, I'll stop and I'll be happy to take questions.
Thank you very much for the very nice talk. I think it was very clear, but perhaps there are some questions, comments. Feel free to unmute yourself or ask questions in the chat if you want. I can read the questions.
So thanks, Aditya, for a nice talk. So I just have one question. Do I understand correctly that so you parameterize the policy, and so you get some kind of transition matrix, which and the entries depend on some parameter. And then you find the stationary probability distribution for that, and then you need a gradient of that with respect to parameter.
Yes.
Yeah. So you can do it with an adjoint method, and I can send you a paper where we do this.
I could imagine, that adjoint methods would also work if I keep track of yes, because I think like if we for the stationary equilibrium case, if there is any adjoint method for the single agent case, that would directly translate to this setting as well to compute the gradients. So those should also work.
But the gradient of the probability of Z, that's what I mean.
Okay, gradient of Z.
Of the single agent.
So, okay, yeah, that would be interesting. So I don't know of adjoint methods to compute that, but if there is something to compute the gradient of the stationary distribution, that solves the technical challenge that we had in the second part.
Yeah. I'll send you a paper because we're looking at something like a stationary distribution of a fluid dynamics model, but mathematically, when you discretize, it's just a Markov transition matrix. So it's the same. Okay.
Okay. Yeah. Thanks. That will be very useful.
Okay, nice. There is Thanos, I think, has raised his hand.
Yes. Thank you for your presentation. It was very interesting. My question would be, could you explain a little bit more the question about exploration exploitation?
Okay. So that's an interesting point, which gets completely hidden under the rug in gradient-based methods. So what is happening for exploration exploitation is that if I go back to my if I go back to my these equations, what happens with the learning rates is that I start with a high learning rate, and then I slowly anneal the learning rate to go slower, such that the sum of alphas goes to infinity, but sum of alpha squares is bounded. And that takes care of the exploration exploitation trade-off in theory. In particular, if I think of alpha n as being chosen as 1 by n, that means that in the beginning I'm putting less weights to my, I move around quite a lot, and as time progresses, I start exploiting more. In practice, using something like 1 by n is very slow. So one uses something like a quasi second order method. In our simulations, we simply used Adam, which is one of the optimizers for gradient descent, which adapts the learning rate on the fly whenever it feels that the curvature of the process is increasing a lot. So from a practical point of view, our experience has been that if we choose initial parameter of something like Adam, if we do a hyperparameter search on that, then we don't have to worry about exploration exploitation trade-offs in gradient-based methods.
Thank you.
Thanks.
Okay, thank you. Maybe Sarah?
Yes, so thank you very much for this presentation. It was very interesting. My question is, what hypothesis do you need for the 2-time scale algorithm, like on the mini-field games?
So I don't remember that on the top of my head. We have that in the paper, but usually what you have is, I may mess this up trying to recall this on the top of my head, but so the 2-time scale conditions imply that this discrete iterations would be tracking 2 ODEs. The one which is moving at a slower time scale assumes that the ODE, in the ODE wherever I have Z, that corresponds to the stationary point of the faster time scale Z. So if I remember correctly, what I need is this faster time scale ODE to have a unique, globally asymptotically stable stationary point, and the slower time scale ODE to have a locally asymptotically stable stationary point. There are also conditions on Lipschitz constants of these gradient estimates, and I guess these the noise in the unbiased gradient estimates should have finite variance. So those are the types of conditions that we have for convergence of 2-time scale algorithms. So part of them are same as what is there for a single time scale algorithm in terms of having locally asymptotically stable stationary point and Lipschitz continuity of the gradient estimates and boundedness of the variance of the noise. The 2-time scale algorithm requires global asymptotic stability of the second ODE, of the faster time scale ODE.
Okay, okay, thank you.
Sure.
Okay, Thank you. More questions or comments? Otherwise, I have some quick questions.
Sure.
Maybe one about the terminology. So what you call local, the term local refers to the fact that you consider just the gradient to be zero.
Yes. Yeah. That
Okay, I see.
if I think of in terms of Nash equilibrium, the usual Nash equilibrium says for all strategies, deviations should not improve performance. And here I'm just saying within a local neighborhood, deviations within a local neighborhood should not improve performance. So that's the rationale for using local terminology. The notion of local Nash equilibrium is already there in general, even normal form games that people have looked at local Nash equilibrium. There are notions of local Markov perfect equilibrium as well. So this is in the same spirit as those.
I see. Yeah, it makes sense. And one quick question about the link with imperfect information. Do you think this could be extended to the, let's say, evolutive or time-dependent, the case where the distribution evolves, or would it be based on the repetition of the game rather than the time steps of the game, or it's a completely different?
I haven't thought about that in too much detail. My immediate gut reaction is that it might actually be just the same argument that if we look at the standard infinite population limit in the evolutive mean field game, that might be viewed as the sequential equilibrium of that imperfect information game. Though there is a catch in taking this viewpoint. So one nice thing when we look at the mean field games equilibrium as a refinement of Markov perfect equilibrium is that we get an epsilon Nash approximation, which is saying that even if players had access to the states of all other agents, they would not have, changing their strategy would not have improved the performance by more than epsilon, which is typically either order 1 by n or 1 by root n. There is no such notion in the imperfect observation case, right? Because it's just, I have imperfect observation, any set of consistent strategy profile and belief system will give me a stationary equilibrium. So in particular, even if I have two players, it's still sequential equilibrium. Although it's not a sequential equilibrium which can be justified too much in a two-player game. So one of the challenges with imperfect information games is that even sequential equilibrium can give rise to solutions which are not good solutions. And people have looked at various refinements of sequential equilibrium to try to avoid those bad equilibria. So one would have to think in terms of, like if you're looking at finite population games in either stationary or the evolutive setting, what would be the right notion there? Which, like, for example, would these be trembling hand perfect equilibrium as well? Which means that if we allow each player to make mistakes, even under that setting, are players playing their best response or not? So each player assumes player will play this strategy, but they will make mistakes. So one might need those types of things to have a complete understanding of how to interpret mean field equilibrium in terms of solutions of games with imperfect information.
I see. Yeah, very interesting. Thank you.
Sure.
Are there more questions?
Oh yeah, fascinating talk, Aditya.
Thanks, Peter.
Great stuff. A couple of questions. Okay, firstly, with your comment about epsilon Nash, it rather points out that, or your remark about it, that points out that there are several aspects to epsilon Nash that the standard interpretation being to what extent the infinite population solution works in the finite population application. And I'm trying to think how that could be interpreted here. Presumably one way would be a robustness interpretation. If the system really isn't or doesn't have an adequate mean stationary behavior, to what extent, if you apply the stationary laws based on the supposition or the derivation that the system has or can be taken to a stationary behavior, how far off you are, but it's a robustness feature there. Or an aspect that one can
Yes. In their paper, Weintraub and all had looked at the notion of what they called, I'm forgetting the term, it's like asymptotic behavior. So they were asking whether one can guarantee that in the limit as n goes to infinity, how quickly do you converge to the stationary distribution, and thinking in terms of robustness with respect to that rate of convergence, which is similar to what you are talking in terms of deviations from that, which would then come back to the stationary distribution with sufficient speed, so to say.
Right. And my other question was really classical notions of controllability and identifiability, which don't often figure in the MDP framework so prominently. And so I just wondered, have questions of unique parameterization identifiability come up with any of the models or examples you've looked at? And the other point is that I know you've got ergodicity of the state space with respect to controls, you can search it out, but if there are any degrees of controllability have ever surfaced or played a role in the analysis. So two classical
So with respect to controllability, the answer is simple, that most of the literature on the first attack on any problem with the MDP approach avoids that by simply assuming either finite state space or compact state spaces, which means effectively uniformly bounded rewards. So there is no notion of instability at all. There are, not in this setting, but in general MDP theory, there is conditions under which MDP models with unbounded reward functions, what are the conditions under which they have a solution? And I think, and those typically rely on having some sort of growth function with respect to which I can take weighted norms of my value functions. And I think those types of methods should be applicable in the mean field analysis as well. And I'm sorry, I forgot your first question.
The identifiability.
Yes, so the identifiability, we didn't really encounter that beyond the fact that we could have multiple equilibrium.
Right.
So yeah. So but that's sort of just the in any local solution concept, or unless we have strong assumptions on the model, equilibriums, there can be multiple equilibrium, and then we are not looking at the question of which equilibrium, how could one focus on a particular equilibrium, or if we think of, let's say this example where there are two equilibrium, if I know this, are there ways to nudge my learning algorithm to converge to the more desirable equilibrium in some sense, since one equilibrium does have a higher payoff than the other? And that I don't know. I mean, that's an interesting question, but I don't know how to do that in these gradient-based algorithms.
Actually, if I could squeeze in monopolize your time for a second, a moment, that might actually bring up the controllability issue. I'm thinking if you have a state space with 1 trillion states, and you're trying to steer around it, or steer a probability distribution over it, that there might be questions of, I mean, with very large finite state spaces, there might be questions, interesting questions of controllability in a classical sense, or in a modernized sense, because you're steering a probability distribution around.
Yes, I think, yeah, maybe if I think of this as a problem of steering the stationary distribution to a desirable setting, then one can pose the controllability question in that setting as well. So that can be an interesting thing. I hadn't thought of it in that light, but yes, I agree that steering the distribution then becomes a continuous valued object, and I need notions of controllability to see if certain stationary distributions are at all possible with certain dynamics or not, and so on.
Great, thanks very much again.
Yeah, thank you.
Okay, nice. More questions? I guess we are a little bit over time, so okay.
If there is time just for one question, I can ask one question, otherwise, yeah.
It depends mostly on the speaker. I'm fine.
Yeah, I'm happy to take questions here.
Okay.
So what is the main difficulty when you're comparing with the time-dependent version? Is it the convergence problem, or is it the memory because you have too many variables, or is the computational complexity? So what is the main bottleneck there?
The main, there in the standard mean field game approach, the evolutive equilibrium is defined as a fixed point between a forward equation and a backward equation. In discrete time, if I think of infinite horizon setting, I'll have an infinite string of things of the mean field in forward time and an infinite string of policies backward in time. So I'll have to do some form of truncation if I want to find that fixed point. So one would have to perhaps instead of looking at infinite horizon, truncate it in some finite horizon and then say something. So when we were looking at it, we did not know how something like this could be done. This is the talk that I gave is based on a paper which appeared in 2019. So we had worked on it in 2018. And since then, there have been a lot of advances in the mean field games literature in terms of reinforcement learning. And now there are different methods in which people have come up with ways to avoid that having to store an infinite trajectory, either by assuming that after a while, the strategies form a certain single parameter class. So for LQG, that they have a certain specific type of behavior. And there are some approximation results also for approximating infinite horizon games by finite horizon games. So some of those things can be used. But even with that, what remains is that the solution that you'll get in the evolutive case is more complicated just by the very construction, right? Because it's a time-varying policy and mean field. So it requires, we haven't done too many simulations on that setting, so I don't know in terms of getting algorithms to work on actual models, how easy or difficult it is to make them to converge. And I think Matthew might have a better answer on that, but we have limited experience in running these algorithms for the evolutive case on practical systems.
Okay,
yes, thank you. I tend to agree with you, and indeed, with a time-dependent component, it gets more complicated from my limited experience. I mean, even from a practical point of view, for example, the 2-time-scale algorithm, it's not so easy to. It's even harder to tune the parameters, etc. So.
Yes.
Yeah, I was just thinking about the turnpike property. So I was just thinking that initialization could be done using a stationary, but I don't know what is the main. Yeah, so that's why I asked. Like.
Yes, yeah, I'm not sure because I'm not 100% on top of the recent literature on RL for mean field games. Like there is a lot of work which has happened in the last 2 years, and there So there may be ways that are there now to avoid that type of things. But you are right that typically, I mean, in an MDP setting, one would expect turnpike-like behavior. So perhaps it could just be broken down into an initialization phase and a steady state phase, or initialization, steady state and end phase. But there are other things also, right? So if you think of an evolutive equilibrium, stationary equilibrium is a special case of that. Let's think of the long-term average setting where it's easier to make these connections. Then stationary equilibrium is a special type of an evolutive equilibrium. But I could also have an evolutive equilibrium where agents settle down into a periodic behavior. And that's not captured by the stationary equilibrium. So I could imagine looking at infinite horizon problems and conjecturing that the equilibrium would be a periodic behavior, and then trying to identify conditions under which that would happen. And so this would be somewhere in between completely time varying and completely stationary. So I think there is a whole spectrum of things which can be done in this space.
Yeah, thank you. Thanks.
Thanks. More questions or comments?
And thanks a lot for all the questions. This was a really good discussion. And
Well, thank you very much.
Do send me the paper. I sort of look forward to that.
Yeah, I did.
Okay.
I did.
Okay, well, yeah. Thank you very much for the very nice presentation.
Thank you.
And thank you everyone for joining.
Thanks.
Thanks very much, Aditya. Thank you.
Thank you.